Hey everybody, this is Mr. Beckstrom, and today we're going to go over section 4.1. This is on maxima and minima. So let's start with some definitions and theorems here, and we'll take a look at the procedure and kind of try to describe what's going on here. So the absolute maximum and minimum says let f be defined on the interval I containing c. If f of c is greater than f of x for every x and I, then f has an absolute maximum value of f of c on I at c, and the same thing is true for the absolute minimum value. And basically that's what that is saying is that if you take some interval, like look at this one here from a to b, and you find some y value for an x value, and that y value is greater than or equal to every other y value on that interval, then that x value is a absolute maximum. And the same thing for the absolute minimum. If you see this c value, this x value here, if you look at the y value where the c is, that's the lowest y value on that interval. So as long as that y value is less than or equal to all other y values on that interval, then we say that an absolute minimum occurs at x is equal to c. And then extreme value theorem says a function that is continuous on a closed interval a to b has an absolute maximum value and an absolute minimum value on that interval. So that if we take any interval, as long as that function is continuous, meaning we can draw a line from the first x value to the last x value, then there has to be some y value that is either the greater. Everything is either greater than or less than that, and we must have a y value where everything is either less than or greater than or equal to that. Gets confusing here. The local extreme point theorem says if f has a local minimum or maximum at c and f prime of c exists, then f prime of c is 0. So if we take a local minimum here, notice that the slope of the tangent line at that local minimum is going to be equal to 0. The slope of the local maximum here is also going to be equal to 0. A critical point, an interior point C of the domain of f. Now an interior point means that it does not include the endpoints, at which the derivative of c is equal to 0 of f of c fails to exist is called a critical point of f. So basically, if there's a point that's either not differentiable, that means that f prime of c fails to exist, or the slope is equal to 0, that's a critical value of the interval there. And lastly, we have a procedure. So assume the function is continuous on the closed interval a to b. Closed means that includes the endpoints a and b. It says locate the critical point c. That's where we have a derivative equal to 0 or a derivative that does not exist. And those points are candidates for the absolute maxima and the absolute minima. That's the maximum point of the interval and the minimum point of the interval. It says evaluate f at the critical points and at the endpoints, and choose the largest and smallest values of f, those are the y values from step 2, for the absolute maximum and minimum values respectively. Alright, so let's go ahead and take a look at a couple of examples to see what all of this means here. Alright, so for this first function here, t over t squared plus 1, I want you to go ahead and find just the critical points of this function here. Find the critical points, and so go ahead, pause the video, try it out, and when you're ready, unpause it and we'll go through the solution. Alright, so remember the critical points is an interior point of the domain, so f at which the derivative is either equal to 0 or it fails to exist. Alright, so the first thing we need to do is find the derivative of this function, and to do that I'm going to go ahead and use the quotient rule, and that says the derivative with respect to t here is equal to the bottom, so t squared plus 1 times the derivative of the top, which is just 1, minus the top, times the derivative of the bottom here, which is 2t, all over the bottom squared. So all over t squared plus 1 quantity squared. All right, let's see if we can clean this up a little bit here. So this is going to be t squared plus 1 minus 2t squared, 2t squared. Let's make sure that's right. All over t squared plus 1 quantity squared. And so t squared minus 2t squared is going to give me 1 minus t squared all over the t squared plus 1 quantity squared. Doesn't look like there's any factoring that we could do. This is a difference of squares right here. So that is 1 plus t times 1 minus t on top, but it's not going to let us cancel out anything here on the bottom. So let's go through and check to see where this function is equal to 0 and where it's undefined. So it's going to be undefined when the denominator is equal to 0. But notice that we're squaring a value and we're adding 1 to it. And when we square a value, that value either has to be positive or it has to be 0. In either case, we're going to get a positive number down here. So there's no possible way to get a 0. Therefore, there's no values of t which make the derivative of this function undefined. So let's see where it's equal to 0 instead of undefined. So if we set this equal to 0, really this fraction here is going to be 0 whenever the top is 0 and the bottom is a non-zero. Well, we've already figured out that there's no values that'll make the bottom 0, so we can just concentrate on the top here. So if I do 1 minus t squared is equal to 0, and we're going to factor this with 1 minus t, 1 plus t is equal to 0, we notice that t can either be positive or negative 1. So those are our two critical values for this one. And if you put this back in, if you have 1 minus positive 1 squared, that's going to be 0, or 1 minus negative 1 squared, that's also 0. So our critical values are positive 1 and negative 1 for this function. All right, let's go ahead and take a look at another example here. All right, for this one here, I want to find the absolute maxima and minima. That means the x value that gives us the largest y value and the x value that gives us the smallest y value on the interval from 0 to pi. All right, so how do we do that? Well, let's kind of go back. Well, first of all, pause the video, see if you can use those procedures to solve it here, and then we'll go over the solution. All right, so remember, we need to figure out what values is the derivative either equal to 0 or it does not exist. Well, the cosine squared of x, just like the cosine of x, is going to be, has the domain of all real numbers. If you remember the curve of the cosine of x, it's going to be something like this, right? That's a horrible, but it's a wave that goes infinitely to the left and to the right. So if we take two values and just multiply them together, we're still going to get a value there. So we're still going to have the same domain. So what do we do here? Well, we need to find out where this function is equal to 0. And in order to do that, we need to, or the derivative of the function. So let's find the derivative. So the derivative is we're going to go ahead and use the product rule for this one. I'm going to do it off to the side here just to show you. So cosine squared of x is really just cosine of x, right, times cosine of x. So it's going to be the first times the derivative of the second. So the derivative of cosine x is negative sine x, plus the second plus cosine of x times the derivative of the first. right, and then so this is going to give us negative sine x cosine x minus sine x cosine x. So this will be minus 2 sine x cosine x. Now we have to see at which values between 0 and pi is this going to give us a 0. So if I set this negative 2 sine x cosine x equal to 0, this is going to be 0 whenever sine of x is equal to 0 or cosine of x is equal to 0. So let's think about where sine of x is equal to 0 on the interval from 0 to pi. So x is going to be equal to, well, the sine of x is equal to 0 at 0 and pi, and the cosine of x is equal to 0 at pi over 2. And this is just using the unit circle here. So here are our 3 critical values there. And we also need to check the endpoints. So I actually have the endpoints here as well. So there's really only 3 values that we're going to need to check on this. So let's go ahead and use our calculator at this point. So let's get out of here, and we are going to change the mode to radian. It's already in radians, so we're good. And then what we're going to do is we are going to put in the original function. So I'm going to put it in like this. Cosine of x, all right, times cosine of x. All right, and put one there like that. And let's go ahead and check our table here. So delete these out. And we just have to check 0, pi, and pi over 2. So 0, pi, so second pi, and pi over 2. Second pi divided by 2. So it looks like we get a absolute maximum at 0 and pi, and an absolute minimum at pi over 2. That means if we take any other values in that interval right there, we're going to get something between 0 and 1. Let's just try it to make sure. Let's say we took like 0.2 times pi, which is in that interval there. 0.2 times pi, second pi, and we get something between 0 and 1. Let's try 0.9 times pi, and sure enough we get something between 0 and 1. So our absolute maximum occurs at 0 and pi, and our absolute minimum occurs at pi over 2. All right, let's take a look at one more example here. Okay, now we have the function of 3x to the 5th minus 25x cubed plus 60x. Write that as y. Go ahead and find the absolute maximum value and the absolute minimum on the interval from -2 to 3. So go ahead and give it a try, and then when you're ready, unpause it, and we'll go through the solution. All right, so this is a polynomial here. So let's go ahead and first find the derivative. So the derivative with respect to x, we're just going to use the power rule, and that's going to be equal to 15x to the 4th minus 75x squared plus 60. Now we're going to set that equal to 0, and I can factor a 15 out of there. So 15, I'm going to have x to the 4th minus 5 x squared, and then this is going to be plus 4. And this is equal to 0. So we can factor this part here. So we're going to get x squared minus 1, and don't forget about the 15 there, x squared minus 4 is equal to 0. So if you set both of these factors equal to 0, you're going to get 4 critical values. So x is equal to positive and negative 1 and positive and negative 2. So we got 4 values, which is right because we have a 4th degree polynomial there. So here's all of the critical values. So what we're going to do now is we are going to plug back in this equation in our calculator and see if these look like minimums or maximums, and we'll check it in. All right, so come up here and let's go to y equals. Let's put in this original equation here. So 3x raised to the 5th minus 25x cubed, x cubed plus 60x plus 60x, and let me make sure that's right. Looks good. So now let's check our table set. Go to our table here. That's the second graph, and I'm going to put all of these values, including the endpoints, in there. So this is, the endpoints are negative 2 and 3. And then we also have our critical values are negative 1, 1, negative 2, but we already have that, and positive 2. All right, so looking at this, the highest y value is when x is equal to 3. So we have an absolute maximum at x equals 3. And then the lowest y value we have is at negative 38. So we have an absolute minimum at x is equal to negative 1. And if we were trying to find the local maximum and minimum here, what I would do is, remember, we only look at interior points. That means points that are not included in the endpoints here, so we can't look at negative 2 or 3. So let's get rid of the negative 2 here and the 3. So delete, delete. And at all of these points, now I'm going to look at my graph here. So at negative 1, we have a local minimum. At positive 1, we have a local maximum. And at positive 2, we have a local minimum. And later on, we'll learn some more ways to calculate that using second derivatives and other methods. But for now, just using my calculator to visually check that is what I'm going to do. All right, guys. I hope this helped. If you have any questions, please let me know, and I hope you have a great rest of your week. Thanks.